more than half of the land surface of the Earth, the temperature rarely falls below the freezing point. On the other hand, we have a globe with the same materials and at the same distance from the sun with a maximum temperature of freezing water, and a minimum not very far from the absolute zero. The monthly mean being probably much below the freezing point of carbonic acid gas, a difference entirely due to the absence of these three favorable conditions. The special features of Mars as influencing temperature. Coming now to the special feature of Mars and its probable temperature, we find that most writers have arrived at a very different conclusion from that of Mr. Lowell, who himself quotes Mr. Moulton as an authority, who recently, by the application of Stephan's law, has found the mean temperature of this planet to be minus 35 degrees Fahrenheit. Again, Professor J. H. Poynting, in his lecture on radiation in the solar system, delivered before the British Association at Cambridge in 1904, gave an estimate of the mean temperature of the planets arrived at from measurements of the sun's emissive power and the application of Stephan's law to the distances of the several planets. And he thus finds the Earth to have a mean temperature of 17 degrees centigrade, and Mars to have one of minus 38 degrees centigrade. A wonderfully close approximation to the mean temperature of the Earth as determined by direct measurement, and therefore, presumably, an equally near approximation to that of Mars as dependent on the distance from the Sun, and on the supposition that it is Earth-like in all its conditions. But we know that it is far from being Earth-like in the very conditions which we have found to be those which determine the extremely different temperatures of the Earth and Moon, and in regards to each of these, we find that so far as it differs from the Earth, it approximates to the less favorable conditions that prevail in the Moon. The first of these conditions which we have found to be essential in regulating the absorption and radiation of heat, and thus raising the mean temperature of a planet, is a compact surface well covered with vegetation, two conditions arising from and absolutely dependent on an ample amount of water. But Mr. Lowell himself assures us, as a fact which he has no doubt, that there are no permanent bodies of water, great or small, upon Mars, that rain and consequently rivers are totally wanting, that its sky is almost constantly clear, and that what appear to be clouds are not formed of water vapor, but of dust. He dwells emphatically on the terrible desert conditions of the greater part of the surface of the planet. That being the case now, we have the right to assume that it has ever been otherwise, and, taking into full account of the fact, neither denied nor disputed by Mr. Lowell, that the force of gravity on Mars is not sufficient to retain water vapor in its atmosphere, we must conclude that the surface of the planet, like that of the Moon, has been molded by some form of volcanic action, modified probably by wind, but not by water. Adding to this, that the force of gravity on Mars is nearer that of the Moon than that of the Earth, we may reasonably conclude that its surface is formed of volcanic matter and a light porous condition, and therefore highly favorable for the rapid loss of surface heat by radiation. The surface conditions of Mars are therefore presumably much more like those of the Moon than those of the Earth. The next condition favorable to the storing up of heat, a covering of vegetation, is almost certainly absent from Mars, except possibly over limited areas and for short periods. In this feature, also the surface of Mars approximates much nearer to the lunar than to Earth conditions. The third condition, a dense vapor-laden atmosphere, is also wanting in Mars, for although it possesses an atmosphere, it is estimated by Mr. Lowell in his latest article to have a pressure equivalent to only 2.5 inches of mercury with us, giving it a density of only 1/12th part that of ours, while aqueous vapor, the chief accumulator of heat, cannot permanently exist in it, and notwithstanding repeated spectroscopic observations for the purpose of detecting it, has never been proved to exist. I submit that I have now shown from the statements, and largely as a result of the long-continued observations by Mr. Lowell himself, that so far as the physical conditions of Mars are known to differ from those of Earth, the differences are all unfavorable to the conservation and favorable to the dissipation of the scanty heat it receives from the sun, that they point unmistakably toward the temperature conditions of the moon rather than to those of the earth, and that the cumulative effect of these adverse conditions acting upon the heat supply reduced by solar distance to less than 1/2 of ours must result in a mean temperature, as well as in the extremes nearer to that of our satellite than to that of our own Earth. Further criticism of Mr. Lowell's article. We are now in a position to test some further conclusions of Mr. Lowell's Philosophical Magazine article by comparison with actual phenomena. We have seen in the outline I have given of this article that he endeavors to show how the small amount of solar heat received by Mars is counterbalanced largely by the greater transparency to light and heat of its thin and cloudless atmosphere, and partially also by a greater conservative or blanketing power of its atmosphere due to the presence in it of a large proportion of carbonic acid gas and aqueous vapor. The first of these statements may be admitted as a fact which is entitled to dwell upon, but the second, the presence of large quantities of carbon dioxide and aqueous vapor, is a pure hypothesis, unsupported by any item of scientific evidence. While in the case of aqueous vapor, it is directly opposed to admitted results founded upon the molecular theory of gaseous elasticity. But although Mr. Lowell refers to the conservative or blanketing effect of the Earth's atmosphere, he does not consider or allow for its very great cumulative effect, as is strikingly shown by the comparison with the actual temperature conditions of the moon. This cumulative effect is due to the continuous reflection and radiation of heat from the clouds as well as from the vapor-laden strata of air in our lower atmosphere, which latter, though very transparent to the luminous and accompanying heat rays of the sun, is opaque to the dark heat rays whether radiated or reflected from the Earth's surface. We are therefore in a position strictly comparable with that of the interior of some huge glass house, which not only becomes intensely heated by the direct rays of the sun, but also to a less degree by reflected rays from the sky and those radiated from the clouds, so that even on a cloudy or misty day its temperature rises many degrees above that of the outer air. Such a building, if of large size, of suitable form, and well protected at night by blinds or other covering, might be so arranged as to accumulate heat in its soil and walls as to maintain a tolerably uniform temperature, though exposed to a considerable range of external heat and cold. It is to such a power of accumulation of heat in our soil and lower atmosphere that we must impute the overwhelming contrast between our climate and that of the moon. With us, the solar heat that penetrates our vapor-laden and cloudy atmosphere is shut in by that same atmosphere, accumulates there for weeks and months together, and can only slowly escape. It is this great cumulative power which Mr. Lowell has not taken account of, while he certainly has not estimated the enormous loss of heat by free radiation which entirely neutralizes the effects of increase of sun heat, however great, when these cumulative agencies are not present. See footnote 12. Temperature on polar regions of Mars. There is also a further consideration which I think Mr. Lowell has altogether omitted to discuss. Whatever may be the mean temperature of Mars, we must take account of the long nights in its polar and high-temperate latitudes, lasting nearly twice as long as ours, with the resultant lowering of temperature by radiation into a constantly clear sky. Even in Siberia, in latitude 67.5 degrees north, a cold of -88 degrees Fahrenheit has been attained, while over a large portion of North Asia and America above 60 degrees latitude, the mean January temperature is from -30 degrees Fahrenheit to -60 degrees Fahrenheit, and the whole subsoil is permanently frozen to a depth of 6 or 7 feet to several hundreds. But the winter temperature over the same latitudes in Mars must be very much lower, and it must require a proportionally larger amount of its feeble sun heat to raise the temperature even to the freezing point, and an additional very large amount to melt any considerable depth of snow. but this identical area from a little below 60 degrees to the pole